Okay. All right. You gave me an amazing tour of Blue Origin rocket factory and launch complex in the historic Cape Canaveral. That's where New Glenn, the big rocket we talked about, is being built and will launch. Can you explain what the New Glenn rocket is and tell me some interesting technical aspects of how it works?
Sure. New Glenn is a very large, a heavy lift launch vehicle. It'll take about 45 metric tons to LEO, very large class. It's about half the thrust, a little more than half the thrust of the Saturn V rocket. So it's about 3.9 million pounds of thrust on liftoff. The booster has 7 BE4 engines. Each engine generates a little more than 550,000 pounds of thrust. The engines are fueled by liquefied natural gas, LNG, as the fuel, and LOX as the oxidizer. The cycle is an Ox-rich stage combustion cycle. It's a cycle that was really pioneered by the Russians. It's a very good cycle. And that engine is also going to power the first stage of the Vulcan rocket, which is the United Launch Alliance rocket. Then the second stage of New Glenn is powered by 2 BE3U engines, which is a upper stage variant of our New Shepard liquid hydrogen engine. So the BE3U has 160,000 pounds of thrust. So 2 of those, 320,000 pounds of thrust. And hydrogen is a very good propellant for upper stages because it has very high ISP. It's not a great propellant, in my view, for booster stages because the stages then get physically so large. Hydrogen has very high ISP, but liquid hydrogen is not dense at all. So to store liquid hydrogen, if you need to store many thousands of pounds of liquid hydrogen, your liquid hydrogen tank gets very large. So you get more benefit from the higher ISP, the specific impulse. You get more benefit from the higher specific impulse on the second stage. And that stage carries less propellant, so you don't get such geometrically gigantic tanks. Mm-hmm. The Delta IV is an example of a vehicle that is all hydrogen. The booster stage is also hydrogen. Mm-hmm. And I think that it's a very effective vehicle, but it never was very cost effective. So it's operationally very capable, but not very cost effective.
So size is also costly.
Size is costly. So it's interesting. Rockets love to be big. Mm-hmm. Everything works better.
What do you mean by that? You've told me that before. It sounds epic, but what's it?
I mean, when you look at the kind of the physics of rocket engines, and also when you look at parasitic mass, it doesn't. If you have, let's say, you have an avionics system, so you have a guidance and control system, that is going to be about the same mass and size for a giant rocket as it is going to be for a tiny rocket, mm-hmm. And so that's just parasitic mass that is very consequential if you're building a very small rocket, but is trivial if you're building a very large rocket. So you have the parasitic mass thing. And then if you look at, for example, rocket engines have turbopumps. They have to pressurize the fuel and the oxidizer up to a very high pressure level in order to inject it into the thrust chamber where it burns. And those pumps, all rotating machines, in fact, get more efficient as they get larger. So really tiny turbopumps are very challenging to manufacture, and any kind of gaps, are like between the housing, for example, and the rotating impeller that pressurizes the fuel. There has to be some gap there. You can't have those parts scraping against one another. Mm-hmm. And those gaps drive inefficiencies. And so, if you have a very large turbopump, those gaps in percentage terms end up being very small. And so there's a bunch of things that you end up loving about having a large rocket, mm-hmm. and that you end up hating for a small rocket. But there's a giant exception to this rule, and it is manufacturing. So manufacturing large structures is very, very challenging. It's a pain in the butt. And so, it's just, if you're making a small rocket engine, you can move all the pieces by hand. You can assemble it on a table. One person can do it. You don't need cranes and heavy lift operations and tooling and so on and so on. When you start building big objects, infrastructure, civil infrastructure, just like the launch pad and all this. We went and visited. I took you to the launch pad, and you can see it's so monumental.
Yeah, it is.
And so just these things become major undertakings, both from an engineering point of view, but also from a construction and cost point of view.
And even the foundation of the launch pad. I mean, this is Florida. Like, isn't it like swampland? Like, how deep you have to go?
At Cape Canaveral.
Yeah.
In fact, at most ocean, most launch pads are on beaches somewhere in the ocean side because you want to launch over water for safety reasons. Yes, you have to drive pilings, dozens and dozens and dozens of pilings, 50, 100, 150 feet deep to get enough structural integrity for these very large, yes, these turn into major civil engineering projects.
I just have to say, everything about that factory is pretty badass. You said tooling. The bigger it gets, the more epic it is.
It does make it epic.
Yeah.
It's fun to look at. It's extraordinary.
It's humbling also because your humans are so small compared to it.
We are building these enormous machines that are harnessing enormous amounts of chemical power, in very, very compact packages. It's truly extraordinary.
But then there's all the different components, and the materials involved. Is there something interesting that you can describe about the materials that comprise the rocket? So it has to be as light as possible, I guess, whilst withstanding the heat and the harsh conditions.
Yeah, I play a little kind of game sometimes with other rocket people that I run into where say, what are the things that would amaze the 1960s engineers?
Mm-hmm.
Like what's changed? Because surprisingly, some of rocketry's greatest hits have not changed. They would recognize immediately a lot of what we do today, and it's exactly what they pioneered back in the 60s. But a few things have changed. The use of carbon composites is very different today. We can build very sophisticated. You saw our carbon tape laying machine that builds the giant fairings, and we can build these incredibly light, very stiff fairing structures out of carbon composite material that they could not have dreamed of. I mean, the efficiency, the structural efficiency of that material is so high compared to any, metallic material you might use or anything else. So that's one. Aluminum lithium and the ability to friction stir weld aluminum lithium. Do you remember the friction stir welding that I showed you? This is a remarkable technology. It was invented decades ago, but has become very practical over just the last couple of decades. And instead of using heat to weld two pieces of metal together, it literally stirs the two pieces. There's a pin that rotates at a certain rate, and you put that pin between the two plates of metal that you want to weld together, and then you move it at a very precise speed. And instead of heating the material, it heats it a little bit because of friction, but not very much. You can literally immediately after welding with stir friction welding, you can touch the material and it's just barely warm. It literally stirs the molecules together. It's quite extraordinary.
Relatively low temperature, and I guess high temperature is what makes them that makes it a weak point.
Exactly. So with traditional welding techniques, you may have whatever the underlying strength characteristics of the material are. You end up with weak regions where you weld. Mm-hmm. And with friction stir welding, the welds are just as strong as the bulk material. So it really allows you, and so because when you're, let's say you're building a tank that you're going to pressurize, a large, liquid natural gas tank for our booster stage, for example, if you are welding that with traditional methods, you have to size those weld lands, the thickness of those pieces, with that knockdown for whatever damage you're doing with the weld, and that's going to add a lot of weight to that tank.
I mean, even just looking at the fairings, the result of that. The complex shape that it takes and like what it's supposed to do is kind of incredible because so people don't know it's on top of the rocket, it's going to fall apart. That's its task, but it has to stay strong sometimes
Yes.
and then disappear when it needs to.
That's right.
Which is a very difficult task.
Yes. When you need something that needs to have 100% integrity until it needs to have 0% integrity, it needs to stay attached until it's ready to go away. And then when it goes away, it has to go away completely. You use explosive charges for that. And so it's a very robust way of separating structure when you need to.
Exploding.
Yeah. Little tiny bits of explosive material, and it'll sever the whole connection.
So if you want to go from 100% structural integrity to 0 as fast as possible, is explosives.
Use explosives.
The entirety of this thing is so badass. Okay, so we're back to the 2 stages. So the first stage is reusable.
Yeah. Second stage is expendable. Second stage is liquid hydrogen, liquid oxygen. So we get to take advantage of the higher specific impulse. The first stage lands downrange on a landing platform in the ocean, comes back for maintenance and get ready to do the next mission.
I mean, there's a million questions, but also, is there a path towards reusability for the second stage?
There is, and we know how to do that. Right now, we're going to work on manufacturing that second stage to make it as inexpensive as possible. There's sort of 2 paths for a second stage. Make it reusable, or work really hard to make it inexpensive so you can afford to expend it. And that trade is actually not obvious which one is better.
Even in terms of cost, even like time,
even in
cost,
terms of cost, and I'm talking about cost. Space flight, getting into orbit is a solved problem. We solved it back in the 50s and 60s.
You're making it sound easy.
The only interesting problem is dramatically reducing the cost of access to orbit, which is, if you can do that, you open up a bunch of new endeavors that lots of startup companies, everybody else can do. So that's one of our missions, is to be part of this industry and lower the cost to orbit so that there can be a kind of a renaissance, a golden age of people doing all kinds of interesting things in space.
I like how you said getting to orbit is a solved problem. It's just the only interesting thing is reducing the cost. You can describe every single problem facing human civilization that way. The physicists would say everything is a solved problem. We've solved everything. The rest is just what Rutherford said, that it's just stamp collecting. It's just the details. Timeline. You said 2024. As it stands now, are both the first test launch and the launch of Escapade Explorers to Mars still possible in
2024?
Yeah.
Yeah, I think so. For sure, the first launch, and then we'll see if Escapade goes on that or not. I think that the first launch for sure, and I hope Escapade too.
Hope.
Well, I just don't know which mission it's actually going to be slated on.
Sure.
So we also have other things that might go on that first mission.
Oh, I got it. But you're optimistic that the launches will still...
Oh, the first launch. I'm very optimistic that the first launch of New Glenn will be in 2024. And I'm just not 100% certain what payload will be on that first launch.
Are you nervous about it?
Are you kidding? I'm extremely nervous about it.
Oh, man.
100%. I've, every launch I go to, for New Shepard, for other vehicles too, I'm always nervous for these launches. But yes, for sure. A first launch, to have no nervousness about that would be, some sign of derangement, I think. So,
well, I got to visit the launch pad. It's pretty, it's epic.
We have done a tremendous amount of ground testing, a tremendous amount of simulation. So, a lot of the problems that we might find in flight have been resolved, but there are some problems you can only find in flight. So, cross your fingers. I guarantee you'll have fun watching it no matter what happens.
100%. When the thing is fully assembled and comes up.
Yeah, the transporter erector, the transporter erector for a rocket of this scale is extraordinary.
That's an incredible machine.
The vehicle travels out horizontally and then kind of comes up
over a few hours.
Beautiful. Yeah, it's a beautiful thing to watch.
You were aboard New Shepard on its first crewed flight. How was that experience? Were you terrified then?
Strangely, I wasn't.
Did you ride the rocket?
It's
Less
true.
nerve-wracking? Okay.
I've watched other people ride in the rocket, and I'm more nervous than when I was inside the rocket myself. It was a difficult conversation to have with my mother when I told her I was going to go on the first one.
Yeah.
And not only was I going to go, but I was going to bring my brother
Yeah.
too. This is a tough conversation to have with a mom.
Yeah, and I mean, there's just a epic nature to it too.
The ascent, the floating in zero gravity. I'll tell you something very interesting. Zero gravity feels very natural. I don't know if it's because we're, it's like return to the womb.
You just confirmed you're an alien, but that's I think that's what you just said.
It feels so natural to be in zero G. It was really interesting. And then what people talk about, the overview effect and seeing Earth from space, I had that feeling very powerfully. I think everyone did. I decided that, first of all, I knew the vehicle extremely well. I know the team who built it. I know the vehicle. I'm very comfortable with the escape system. We put as much effort into the escape system on that vehicle as we put into all the rest of the vehicle combined. It's one of the hardest pieces of engineering in the entire New Shepard architecture.
Can you actually describe what you mean by escape system? What's involved?
We have a solid rocket motor in the base of the crew capsule, so that if anything goes wrong on ascent, while the main rocket engine is firing, we can ignite this solid rocket motor in the base of the crew capsule and escape from the booster. It's a very challenging system to build, design, validate, test, all of these things. It is the reason that I am comfortable letting anyone go on New Shepard. So the booster is as safe and reliable as we can make it, but we're harnessing, whenever you're talking about rocket engines, I don't care what rocket engine you're talking about, you are harnessing such vast power in such a small, compact geometric space. The power density is so enormous that it is impossible to ever be sure that nothing will go wrong. Mm-hmm. And so the only way to improve safety is to have an escape system. And historically, rockets, human-rated rockets, have had escape systems. Only the space shuttle did not. And but Apollo had one. All of the previous, Gemini, etc., they all had escape systems. And we have on New Shepard unusual escapes. Most escape systems are towers. We have a pusher escape system. So the solid rocket motor is actually embedded in the base of the crew capsule, and it pushes. And it's reusable in the sense that if we don't use it, so if we have a nominal mission, we land with it. The tower systems have to be ejected at a certain point in the mission. And so they get wasted even in a nominal mission. And so again, cost really matters on these things. So we figured out how to have the escape system be a reusable, in the event that it's not used, you can reuse it, and have it be a pusher system. It's a very sophisticated thing. So I knew these things. You asked me about my decision to go. And so I know the vehicle very well. I know the people who designed it. I have great trust in them and in the engineering that we did. And I thought to myself, look, if I am not ready to go, then I wouldn't want anyone to go. A tourism vehicle has to be designed, in my view, to be as safe as one can make it. You can't make it perfectly safe. It's impossible. But, you just have to, people will do things, people take risk, they climb mountains, they skydive, they, do deep underwater scuba diving and so on. People are okay taking risk. You can't eliminate the risk, but it is something, because it's a tourism vehicle, you have to do your utmost to eliminate those risks. And I felt very good about the system. I think it's one of the reasons I was so calm inside, and maybe others weren't as calm. They didn't know as much about it as I did.
Who was in charge of engaging the escape system? Did you have?
It's automated.
Okay.
The escape system
I was visualizing a
is
button. I'm sorry.
completely automated. Automated is better because it can react so much faster.
So yeah, for tourism, rockets, safety is a huge priority for space exploration also, but a tiny, a delta less.
Yes, I mean, I think for, if you're doing, there are human activities where we tolerate more risk. If you're saving somebody's life, if you are, engaging in real exploration, these are things where, I personally think we would accept more risk, in part because you have to.
You've mentioned the lunar program. Let me ask you about that.
Yeah.
There's a lot going on there, and you haven't really talked about it much. So, in addition to the Artemis program with NASA, Blue is doing its own lander program. Can you describe it? There's a sexy picture on Instagram with one of them. Is it the MK1, I guess?
Yeah, the Mark One.
Yeah.
The picture is me with Bill Nelson, the NASA administrator.
Just to clarify, the lander is the sexy thing about the Instagram. Really want to clarify
I know it's
that.
not me. I know it was either the lander or Bill.
Okay.
Hey,
I love
thank
Bill,
you for
but
clarifying.
okay.
Yes, the Mark One lander is designed to take 3,000 kilograms to the surface of the moon in expendable cargo. It's an expendable lander, lands on the moon, stays there, take 3,000 kilograms to the surface. It can be launched on a single New Glenn flight, which is very important. So it's a relatively simple architecture, just like the human landing system lander that they call the Mark II. Mark I is also fueled with liquid hydrogen, and which is for high energy missions like landing on the surface of the moon. The high specific impulse of hydrogen is a very big advantage. The disadvantage of hydrogen has always been that it's since it's such a deep cryogen, it's not storable. So it's constantly boiling off, and you're losing propellant because it's boiling off. And so what we're doing as part of our lunar program is developing solar-powered cryocoolers that can actually make hydrogen a storable propellant for deep space. And that's a real game changer. It's a game changer for any high-energy mission, so to the moon, but to the outer planets, to Mars, everywhere.
So the idea with Mark 1, both Mark 1 and Mark 2, is the New Glenn can carry it from the surface of Earth to the surface of the moon.
Exactly. So the Mark I is expendable. The lunar lander we're developing for NASA, the Mark II lander, that's part of the Artemis program. They call it the sustaining lander program. So that lander is designed to be reusable. It can land on the surface of the moon in a single stage configuration and then take off. So if you look at the Apollo program, the lunar lander in Apollo was really two stages. It would land on the surface, and then it would leave the descent stage on the surface of the moon, and only the ascent stage would go back up into lunar orbit where it would rendezvous with the command module. Here, what we're doing is we have a single stage lunar lander that carries down enough propellant so that it can bring the whole thing back up so that it can be reused over and over. And the point of doing that, of course, is to reduce cost so that you can make lunar missions more affordable over time, that's one of NASA's big objectives, because this time, the whole point of Artemis is go back to the moon, but this time to stay. Mm-hmm. So, back in the Apollo program, we went to the moon 6 times and then ended the program, and it really was too expensive to continue.
And so there's a few questions there, but one is, how do you stay on the moon? What ideas do you have about like a sustaining life where a few folks can stay there for prolonged periods of time?
Well, one of the things we're working on is using lunar resources like lunar regolith mm-hmm. to manufacture commodities and even solar cells on the surface of the moon. We've already built a solar cell that is completely made from lunar regolith simulant. And this solar cell is only about 7% power efficient, so it's very inefficient compared to the more advanced solar cells that we make here on Earth. But if you can figure out how to make a practical solar cell factory that you can land on the surface of the moon,
Mhm.
and then the raw material for those solar cells is simply lunar regolith, then you can just continue to churn out solar cells on the surface of the moon, have lots of power on the surface of the moon. That will make it easier for people to live on the moon. Similarly, we're working on extracting oxygen from lunar regolith. So lunar regolith by weight has a lot of oxygen in it. It's bound very tightly, as oxides with other elements, and so you have to separate the oxygen, which is very energy intensive. So that also could work together with the solar cells. But if you can, and then ultimately, we may be able to find practical quantities of ice in the permanently shadowed craters on the poles of the moon. And we know there is ice water in those, or water ice in those craters. And we know that we can break that down with electrolysis into hydrogen and oxygen. And then you'd not only have oxygen, but you'd also have a very good high efficiency propellant fuel in hydrogen. So there's a lot we can do to make the moon more sustainable over time. But the very first step, the kind of gate that all of that has to go through, is we need to be able to land cargo and humans on the surface of the moon at an acceptable cost.
To fast forward a little bit, is there any chance Jeff Bezos steps foot on the moon and on Mars? One or the other or both?
It's very unlikely. I think it's probably something that gets done by future generations by the time it
Right.
gets to me. I think in my lifetime, that's probably going to be done by professional astronauts.
Hmm.
Sadly, I
Yeah.
would love to sign up for that mission. So don't count me out yet, Lex. Give me a
Yeah.
fighting shot here, maybe.
Yeah.
But I think if we are placing reasonable bets on such a thing in my lifetime, that will continue to be done by professional astronauts.
Yeah. So these are risky, difficult missions.
And probably missions that require a lot of training. You are going there for a very specific purpose to do something. We're going to be able to do a lot on the moon too with automation. So, in terms of setting up these factories and doing all that, we're sophisticated enough now with automation that we probably don't need humans to tend those factories and machines. So there's a lot that's going to be done in both modes.